we could say about about series today. Okay, so we want to talk about series. Start to talk about a unit called series, but don't worry, we're not going to deal with any series really today yet. Okay, we'll deal with infinity, but we always deal with infinity. That's not a big deal. Okay. So our first section for this unit is improper integrals. It might seem a little disconnected because it's a series unit, but it'll come back for us like right away. This will come back right back to us and be useful, I promise. So this is a kind of integral that we just have avoided showing you so far. Okay, let's start with this little experiment. Can you guys do some of these integrals with your calculator? Now it'll be pretty quick for you to do these. Just FN in these. It'll be pretty quick to do these. By the way, you could do them with by hand too, right? Just a little U-Substitution. And just as you do them, do you know how to recall the thing you just typed in? And type it in again. Then just change the upper limit. Do you notice? It shouldn't take you long to do these because each one is exactly the same minus the upper limit. Yeah. We're going to try and get one. Yeah, so we have one plus another. We're going to give you another test grade. You'll see. Based on the review stuff. How's it going out there? It's definitely increasing, right? True. If you want to have fun, then try like instead of 10, try 100 and see what happens. Becoming closer and closer to something. In general, I'd like to ask this question: what would you like to assign the value of this set of symbols? I mean, right now, this set of symbols may have no meaning to you, and yet it seems like we should maybe attribute the value, what? 2 to this. Like maybe this is meaningful, and maybe for some of you that are like already trying to think about why this isn't a series unit, like maybe you already even thought about this. You're like, remember the idea of an infinite series? Maybe this is like that, but the continuous case. If maybe we can think about this. You remember like summing, it was your first time last year in pre-calculus, you realized that you could sum an infinite series, and that was like a meaningful thing.
Crazy.
Like for that summation symbol, which we're going to get used to using all the time in this unit. That summation symbol, it like maybe didn't make sense the first time you saw an infinity above that, but then eventually you became more comfortable with that. Well, that's the same kind of thing happening here. You're like, I'm not comfortable seeing an infinity up there, but it's okay. You'll become comfortable with it. It's all right. Here's how the work goes to show you that this is equal to like proving it from the calculator. Here we go. Right? What does it mean to go to infinity? Like it means that we take the upper limit and do what we just did. Do you feel like what we just did? What is it that we were just doing? We were letting it be a number, and then in the end we were like, well, what happens when that number goes to infinity? So this first thing says nicely what you were doing intuitively with your calculator, right? It's like doing exactly what it said. Put a number in here. I don't know what to do with infinity, but I'm good with like 1,000,000. You can ask me about that. And now this completely makes sense to us. A second ago it was like, I don't know what that means. And now it's like, everything there I do know what it means. I'm just going to keep this limit as a approaches infinity as like reserved out in front for now. I'm just going to resolve all the other stuff using calculus I know. Just using a little U-Substitution there. Just by inspection, you could probably do that antiderivative. Plug in a, plug in 0, subtract. And then this last step, because it's been a while maybe since you've thought about limits, can you explain why this last step comes out to be 2? Yeah, this first thing goes to 0, doesn't it?
Wait.
That first expression, when a is large, you're just thinking about that exponential thing. What happens when a is large? The exponent becomes some really large negative number. So therefore this piece goes to 0, and 2e to the 0 doesn't even involve a, that is 2, right? Is that cool or what? I mean, we should just step back and appreciate the fact that there, inside of 3 minutes, we just like evaluated our first improper integral, it's called. Okay? I have to say there? Oh yeah, and by the way, we should say, just like when eventually we'll use the same terms with series, and really, maybe this is a series in the infinite continuous case. We're going to say that this particular integral converges. We should take for granted the fact that this happened, right? It's not necessarily going to happen always. When we go through this process, if you just give me a random function of some type, like how about e to the x over 2 rather than e to the negative x over 2, then I think you'll find that that one will diverge horribly. That's terrible. So the fact that this even happens is maybe like a little bit lucky for us, right? And we might start to ask, in which situations will this happen? Well, they're exactly the situations in which when we get to this step in the process and we evaluate the limit, we get a number, or maybe we don't, right? So we've reduced it to like a limit question for first semester. Do you know how to take this limit? If so, take the limit. See what you get. If you get a number, you've just evaluated the integral. If you get something that's not a number, then it diverges. Yeah, you get infinity or undefined. This, yeah, we haven't talked about that at all right now. I'm just like saying, how do we evaluate this limit? You'll see that those come in, though. You'll even today, you'll start to see that. All right, so evaluate this integral, or maybe it diverges, right? I don't know. Let's see. But you should, yeah. Don't forget what you just said. That's going to come back, absolutely. So what are we doing? Again, I don't know how to deal with the negative infinity, so maybe I write, what's your favorite letter?
B.
B? A B, like a capital B then? Is that what you want?
Yeah.
Okay, capital B. Okay, because that's Michael's grade. Okay, all right. But wait, we want to take the limit of this expression as B, capital B, goes toward, this time, negative infinity, right? Does that make sense? That's a B. You can use whatever letter you like in your own notes. This limit as B approaches negative infinity will just hang out in front of this as we do this. Did I already mention today that you can't forget anything ever? Did I already mention that? Okay, because I need you to give me the antiderivative of this. Maybe it's not obvious. No, I don't like maybe we need to look at this just a slightly different way. I really don't like that 4 there because I do like when I see an x squared plus 1 in the bottom, don't I? Because it's tan inverse, right? So I'd like that to be a 1. So I'm going to divide through by 4 on the top and bottom of this fraction. Up top I'll get 1/2. And on the bottom I'll get x over 4, x squared over 4, plus 1 dx. And believe it or not, that's a better situation. And do you mind a little magic eraser in here? You like that?
I like that.
Okay. Why? And you could use some U-Substitution if you like. Oh, actually, maybe I'm done. Maybe I already have the integral. What is it? What is that going to be? It's tan inverse of something. Yeah, maybe. Check that on us here. D to 2. Did we get it? Is that right? I mean, just take the derivative quickly. The derivative of tan inverse is 1 over x over 2 squared plus 1. And then times 1/2 by the chain rule.
Yeah.
Does that work? Yeah.
What about the 1/2 from the numerator earlier?
Yeah, actually, we like the fact that it's there. Like it was me being nice to you that I put that there, actually, because when you do U-Substitution on this, like that needs to be there. You'll see. Like let's take the derivative again in our heads. The derivative of tan inverse of x over 2 is 1 over x over 2 squared plus 1. But then wait, times, we forgot, times 1/2. Perfect. It's in the numerator. So actually, I think that works out nicely for us. You can go and do the U-Substitution off on the side, and you'll get the same thing. That's not the focus of today's lesson, so go back and actually understand that, please, at some point. Make sure you remember how to do that. All right, this is the interesting part, though. We want to actually think about evaluating that limit. So we have, let's still write this out here. What do we have? Tan inverse of 1 minus tan inverse of b over 2. I guess I should use the same grouping symbol here. And now we plug in negative infinity. By the way, what's the tan inverse of 1? Yeah, pi over 4. And what happens for the inverse tangent? For me, this is helpful if I understand and remember what the graph of inverse tangent looks like a little bit, but you don't have to. As b goes toward negative infinity, I'm basically asking you, what's the inverse tangent of negative infinity? What is the inverse tangent of negative infinity? Negative pi over 2. And like again, for me, I'm just thinking graphically on it. The inverse tangent function looks kind of like this, right? And it has asymptotes here and here at pi over 2 and negative pi over 2, right? Yeah, it's inverse tangent. So now, with that picture, is it pretty clear that as b goes toward negative infinity, that function goes toward negative pi over 2? So we have minus negative pi over 2. So we get 3 pi over 4 as our answer. All right, cool. So it does converge to 3 pi over 4, we would say. This integral equals 3 pi over 4. And again, you could quick check that using f and n, but instead of negative infinity, maybe you plug in, negative 1,000 or something, and see that you get, and then plug in your calculator 3 pi over 4 and see if you get something similar. Are we having fun yet? Okay. Yeah. Yeah, there's a little more to the story, but that's an obvious case. If you see infinity or negative infinity on the top or bottom limit of integration, then it's definitely improper. But there's one other case that we haven't talked about yet today, and I'll introduce those soon. Someone can check our answer with that. I don't know whether we got it right or not, but okay. Let's try another one. How do we deal with this situation? Alana already knows. Because she read ahead. You thought about it. This time the integral, the limit, that's not the interesting part. It's this first play here. This is the first play that we want to care about. Yeah, maybe we need to split this up in two pieces, right? Okay. So what's your favorite number? Doesn't matter. How about 0? Okay. So how about we take the limit, how about we split this up from negative infinity to 0? And from 0 to infinity. And now we've reduced this successfully to a previously solved type of question, right? And so actually we can, well, because we don't know how to take two limits at once. Limit as, this time we'll use m, how about? M goes to negative infinity, and over here we'll use, how about n? N goes to positive infinity. All right. We get the inverse tangent again. It's beautiful. So feel free to work that out. I actually don't really want to. You can do it yourself. What do you think you'll get in the end on this one? I mean, let's see. Let's actually do it. Okay. What do we get? Tan inverse of. Can I just say m as m goes to negative infinity? Is that too much all at once? Yeah, it's basically the same. That's what I said. I hesitate to even do this again, but we'll do it. I'm skipping a little bit there, right? I'm kind of compacting my work. Sorry. So what does this come out to be? Oh, and actually, yeah. This is minus. Sorry, I did that too quickly. This should be negative tan inverse of m, because it'll be tan inverse of 0 minus tan inverse of m. Is that all right? Over there, I think we're good, though, because it's minus tan inverse of 0, so I think we're good. So again, maybe think of that graph in our minds. What does that come out to be? As we go toward negative infinity, we already asked that question. It'll be negative pi over 2, but except, the positive pi over 2. And did you expect this to happen? What do you get over here? Why? By the way, why do I expect actually to get the same value for both of these integrals? Yeah, the original function. Yeah. Because there's an x squared in it? Okay, there's a name for that too. That particular function we started with is an even function. So actually we expect the area on the left and the area on the right to be the same. So anyway, did you see that coming? Pi. The area under this curve is pi? What? Yeah. By the way, this is an appropriate time to let me close the door so Miss Kathy can hear. So make fun of statistics a little bit. Okay. Right. Some of you are in AP statistics class, and I'd love you to tell me what this integral evaluates to. Oops. That's supposed to be a 2 there. It's 1 because what is this curve? It actually, by the way, it looks almost identical to this one. Yeah, this is the normal distribution. It has any probability density function. It should have, if it really is a probability density curve, it should have area underneath of it 1. Okay, so we should have mentioned this maybe earlier on when we were doing integration. If we had made it in my class, maybe I did. But anytime you're computing an integral, anytime you're doing you're calculating the area under a curve in statistics class, you're doing calculus, and they just never told you, and that's like a crime, isn't it? Isn't that like a crime? Like, what do you think the integral of this is here? Change this from -1 to 1 instead. People who know stat, what is that?
Oh, that says between z squares 1 negative.
What is it?
65.
I think it's 68.5. Rather, 0.685. Yeah. Right. So now instead of using for stat people, never ever use normal CDF. Be the nerd instead who does this every time. Just use F and N. That's all you need. You don't need stat. All you need is calculus. Okay. Is that fair? I just think they should make people credit. I just wanted to speak my piece. I'm coming down now. I'm coming back down off the soapbox. I'm sorry. Okay. I just a crime that you're taking integrals every day, and even some improper integrals. What? And they don't even tell you that you're doing calculus at every turn. Every day in stat class, you're doing calculus, but they're just let's just use this black box. Anyway. All right, let's keep going. How about this one here? This one looks like a nice reprieve from some of the ones we've been doing. 1/x. My favorite letter today is J. Sorry. All right. Oops, that was supposed to be a J. Went out of my way to make that a J. I love this, right? Because I think what's the derivative? What's the antiderivative of 1/x? Yeah, and by the way, why is it okay if I just say ln x and not ln of absolute value of x?
Because it's 1 to J.
Why is there no need for absolute values there? Yeah, because we're only ranging over positive values for this integral. So we can be a little cavalier. All right, so lnj minus ln1. Yeah, there's a 1 on the bottom because, like, I told you so. What's ln1? I like that one. That's 0. What's ln of infinity, though? So this is 0, but this is infinity. Now, it's infinity slowly, right? But it's still infinity, okay? So this is our first example of an integral that we would say diverges. Yes, Jack?
What other values do you get as an answer that constitute divergence?
How about negative infinity?
Are those the only two currently?
You could also have something that makes like no sense and goes positive and negative on you and oscillates or something like that too. I think in almost every case we'll give you, that's what will happen though. Okay. All right. Next type of asymptote. Next type of improper integral is one that maybe doesn't seem like one at first. And this goes back to answer whoever's question who asked me, will there always be infinity or negative infinity up at the top or bottom of the integral? And that is an obvious case where like, oh, improper integral. But this is like sneaks up on you. Someone just throws this integral at you and you're like, sweet, I can do this with like first semester knowledge, 0 and 1. But what happens? What's going on? In fact, before you ever do any calculus, you should make this observation. Do you see it? I mean, I have it up here, and we're in this lesson, so you're in tune for this. But what's happening that's weird here? Just come from the pre-calculus angle on this. What's happening? It says right here, integrands with vertical asymptotes at the limits of integration. Yeah, at 0, we have a vertical asymptote on the original function. So already our alert bells are kind of ringing on this. We're like, whoa, wait, what? How can we even do that? Can we integrate next to an asymptote? And the answer is maybe, I don't know. How do we deal with that situation? Oops. Let's take the same approach here. Let's be like, I'm not sure. But I do know how to integrate from, what's your favorite letter? No, pick a new one. H? Okay. The limit as h goes to what? Yeah, we want h to approach 0. From, let's be more specific, from the right. Maybe that'll matter, maybe not. Okay. We want, the point is I know how to take an integral like 0.1 to 1, right? Or 0.0001 to 1. I'm good with that too. So what are we doing? We're letting this lower bound get closer and closer to 0 from the right. Okay? Just want to make sure that's clear. All right, and then I think once that's been established, I think you're like in the clear now. So let's keep going. That was like the interesting part. The rest is, I think, going to go well. We'll see. We'll see how it goes. I'm like having trouble with the pre-calculus here, so give me a second. I need to like see that right there like that. So does that come out nicely? Yeah, x to the 1/2. With a 2 out front. Okay. Catch us in if there are any arithmetic errors along the way, right? And then, yeah, so I think that's just a square root, so it's going to be 2. Well, we'll plug it in. It's 2 times the square root of 1 minus 2 times the square root of h. Come up here. So that's 2 minus 2, and I can take the limit of this expression, the square root of h, if we're approaching 0 from the right, it's 0. So I think we're good. I don't think I needed to use that arrow. I could have just written that 2 there, yeah. Yeah, we can't, this integral isn't even defined. If someone asks you, like, you can even use pre-calculus to weed that out. Like, if someone asks you, integrate this from -1 to 0, you're like, there aren't even ever any f of x values at all for values like -1 or -1/2 or like nowhere in there is it even defined, right? Like the graph looks like this. So we just computed, in case you were wondering, we just calculated the value under this curve. This infinite amount of area right here, except it's not infinite, it's an infinite region, but it converges to the value 2. You could paint it with a finite amount of paint, right? Yeah.
No, it
It says evaluate it, or if you can't evaluate it, show that it diverges. So both of those follow the same process. That's the only instruction I've given you so far today is evaluate or show that the integral diverges. So in this case, for example, we evaluated it, but if we got infinity, then we say it diverges. So we just proved that it diverges. Yeah, Andrew. Ah, sorry. Which one, Andrew? Yeah. Yeah, there's and you can look this up if you like. Gabriel's horn deals with surface area and volume, but it would be an interesting thing to think through here, whether there's such a thing that has an infinite, and this is true. This is a little bit beyond the scope of the class because I talked about surface area, but I said we wouldn't actually go into calculating surface area. But feel free to look up Gabriel's horn. Gabriel's horn feels paradoxical. It's really not actually, but it sounds strange to you to hear this. Gabriel's horn is a solid revolution that you can calculate the volume of, and the volume is finite. Excuse me. The surface area is infinite. Could you do something with Gabriel's case? I want to say it right here. The surface area is infinite, but the volume is finite. So that means you can. That means that seems like a little bit counterintuitive that could be true that you have like a solid that has a finite volume, but it's a surface area. Huh? Yeah, you could do it with improper integrals, exactly. Yeah. I think it's actually at the end of this section in your book. You can look at there's like a call out or whatever, and you can look at it if you like. Gabriel's horn is very, very, very interesting. All right. Type 3. Let's at least set this up before you head out. Sorry, we got a little distracted there. How do we deal with this? I mean, already maybe I've kind of given it away with the title there, but why is this even? You look at this and you're like, again, this looks simple enough. Seems like there's nothing improper about this, and yet you need to use some pre-calculus knowledge to make what observation? There's a vertical asymptote for this function at x equals 1, right? So we need to be like really careful there, and the way we'll do that is by integrating from 0 to 1 this function and reducing this to 2 of the previous kinds of problems, right? And then 1 to 3. And then again, what's our favorite letter instead of 1 here? Q this time. I like it. And what we need to attach a symbol here to it. Wait 1 second here. This is Q from the left, and this is Q from the right. So we're just going to be careful about that when we come to that situation finally at the end of this problem. We're going to have to be careful taking that limit. All right, and then we can keep going here. The bell is going to ring in a second here, but that's the setup. I would never erase something. We will continue talking about series and improper integrals on Wednesday.